380 and analytical chemistry with many of you who are in the audience. And she was like, should I be math? Should I be chemistry? What should I be? And we had many conversations, and it really is my privilege to have worked with her in her time here. I find her an inspirational scientist, an inspirational person, just an inspiration overall. She is going to head to join the Peace Corps and teach chemistry in Mozambique. Got that right?
Yep.
Okay. Just a really exciting time. This project really stemmed from, we kind of did some analytical chemistry, and then she went off to Cornell and did some more food science chemistry with GC olfactory to look at wines. And then Bobby Fleshman had created a set of barrels that just really fit Issa's interests, and I just think this is a really unique opportunity where we had the right project, the right people, and the right student, and I hope you enjoy what she produced. That's all I have for you.
Okay, so I'd like to thank my advisor, Deanna, for that, and I also worked very closely with Bobby Fleshman on this project, kind of my advisors, and as Deanna mentioned, they kind of came to me in September with this idea of working with barrels. Like, it fit with my food science interests. It's more of like a quality control project, and the idea was like, okay, we're going to kind of take this easy. Like, it'll be a nice way to finish off your senior year. But it ended up being a lot more complex than that. Beer, very complex. You've got yeast. In our case, we've got bacteria also in our beer. So there's a lot of living things, a lot of non-living things that are interacting, and it's just very difficult to understand in general. We've been brewing for thousands of years, but we've only recently been studying beer. So that's kind of where a lot of these questions stem from. So before I dive into my own research, I think it's important to understand the brewing process. So we're going to quickly go through that. It's a little daunting, so I'm going to break it down, start with the top half. So beer starts with barley. We first allow our barley to germinate, and then we dry our barley out. You crush it. This is called the milling process, crushing the barley into powder. Then you mix the barley with water to create mash. And during this process, the enzymes in the grains will convert starches into sugars, and this will give us our wort once we separate out the used grains. So our wort is our sugary liquid. At this point, the wort kettle, we add hops to our boiling wort to impart more bitter flavors. After that, we separate out the wort in the whirlpool, and we allow our hopped wort to cool. Okay, then we're over here on the right side. We add yeast to our hopped wort, and this begins the fermentation process. Fermentation, the yeast are converting the sugars into alcohol and carbon dioxide. We're also producing some acids. From there, we can put our beer into a resting tank, and this is the aging process. This is where all my research is focused, in the aging process. And this looks different for different beers. So for an ale, you might age for 1 week, a lager 2 weeks, for a sour beer many months, so it looks different for different beers. From there, you filter out the yeast, and you're ready to bottle your beer, package it, drink it. That's the process in a nutshell. So the research started again. Deanna and Bobby approached me with this idea. Bobby had made a lot of beer. There's 10 barrels of beer in the basement of Appleton Beer Factory right now. 5 of those barrels are French oak, 5 are American oak. And they're in this giant box that is temperature and humidity controlled. And all of them were made from the same ale recipe to begin with. So this is a super controlled environment, and I didn't realize it at the time, but you don't see this kind of setup in breweries, hardly ever. So it's the perfect place to start for an undergraduate research project. So my plan was to conduct exploratory research. So this is casting a really wide net. We don't know what we're going to find. I think the general idea was to come up with a quality control system that brewers could use on their own. But really, besides that, we didn't have much direction. So we decided to start with a really good question, which is, how do these barrels change over time? Again, that's really broad, so we need to narrow it down just a little bit and decide what we're actually going to measure. And we decided on pH, specific gravity, and titratable acidity data. And I'll get into what those mean in this background information and theory section. First, though, I'm going to explain the difference between a clean fermentation and a mixed fermentation. Because as you saw in my title, I'm concerned about mixed fermentations. After that, I'll go through the definitions of the parameters I just noted. Okay, so clean fermentation, this is your everyday ale or lager, your PBR, your spotted cow, like probably what you're drinking. And it's considered clean because you want to keep it free of contaminants. And when I say contaminants, I mean bacteria that are going to create like nasty flavors in your beer. So we ferment only with yeast, and the fermentation will take about 8 to 10 days, and we're aging for a short period of time, 1 to 2 weeks. Okay, now mixed fermentation is different, and it's mixed because of the combination of yeast and bacteria in the fermentation process. So typical yeast that you use are Saccharomyces and Brettanomyces. Typical bacteria are Lactobacillus and Pediococcus. So a little more about the bacteria. They're both under the larger category of lactic acid bacteria. Both are facultative anaerobic organisms, which means they can survive in oxygen-poor and oxygen-rich environments, and I'll get a little more into that later on. Lactobacillus are characterized by their rod shapes, as you see in this gram stain. Pediococcus, known for their spherical shapes, and they kind of like to cluster in groups of about 4, although they don't have to. Okay, so back to the mixed fermentation slide. Mixed fermentations are known for being like acidic and tart tasting. That's where the name sour beer comes from. So if you haven't heard of mixed fermentation, you've probably heard of sour beer. And they'll go through many rounds of fermentation. As I mentioned, there's the yeast, there's the bacteria. And in our case, our beer is aging in oak barrels. And this process is taking a very long time. So I think Bobby made the beer in July, and it's been aging ever since. Okay, just a recap of clean fermentations versus mixed. In clean fermentations, we only use yeast. Mixed, we use yeast and bacteria. For clean, we only go through primary fermentation. Mixed, we'll go through primary, secondary. Aging is much shorter for clean, very long for mixed. And now I'm going to introduce this idea of pH. So for a clean fermentation, your finished beer will have a pH of between 3.8 and 4.5, and a mixed fermentation will have a pH between 3.3 and 3.6. So sour beers are more acidic and have a lower pH. So more on pH. It's really a measure of acidity. It's a measure of the hydrogen ion concentration, and I'm sure most of you have seen the equation pH equals negative log of the hydrogen ion concentration. And it's only a measure of the dissociated hydrogen ion. So if you take a look at this dissociation of a weak acid, we're only measuring the H+ that's on its own. This is a scale of pH, and it's a little counterintuitive because the more hydrogen ions you have, the lower pH you'll have, more acidic. The fewer hydrogen ions you have, the higher the pH, the more basic. It's kind of how the scale works. Okay, titratable acidity is another way to measure acidity. It's just a little different. So where pH only takes into account the dissociated hydrogen ions, titratable acidity measures both the dissociated and the bound hydrogen ions. I'm going to note here that for the sake of this talk, I'm using the terms titratable acidity and total acidity kind of interchangeably. The debate is still out on that. Sometimes scientists are like, no, they're absolutely different things, but they definitely correlate, and according to the American Association of Brewing Chemists, we can use the two interchangeably. So I will be doing that. Why do we measure titratable acidity? We taste both the bound and the dissociated hydrogen ions. So if we want to quantify something that we're tasting, this might be the way to go. In general, pH alone isn't giving us the full story. So what do we expect to see over time? How does pH change over time? How does titratable acidity or total acidity change over time? pH should decrease, total acidity should increase. And this is based on clean fermentations. So although we're working with mixed fermentations, this is kind of what I was expecting going into my research. Specific gravity is another important term. It's really comparing two densities, density of one material compared to another. So in our case, our material is beer, and we're comparing it to water. So it's really just the ratio, the density of beer compared to the density of water, and it's unitless. It's important because it goes into our calculation for total acidity. It's also important because it gives us a percent alcohol by volume. That's like one way to calculate it. So you can use your final specific gravity compared to your original specific gravity, multiplied by a constant, and you'll get your alcohol by volume. And then this scale is just kind of giving you a little context. So ethanol is less dense than water, hence the small specific gravity. Unfermented wort is more dense than water, hence the larger specific gravity. Okay, and during the fermentation, this is the trend that you'd expect to see for specific gravity. So it will decrease as your percent alcohol. Your percent, yes, alcohol or ethanol will increase. Okay, now on to methods. So what did I actually do? I'll start with sampling and how I sample. Go to the brewery, then what do I do? That's what I'll be answering here. So I'll talk about some on-site tests and the sampling techniques I used. Then once I collect my samples, I bring them back to the lab, and that's where I do titratable acidity experiments. And finally, I'll talk a little bit about the detection of bacteria. So this is in the basement of Appleton Beer Factory. This is the box that Bobby made, and it's the home to our 10 barrels. There's me, and there's Larissa, who is my sampling assistant, I would call her. And this is the front end of the barrel, back end. So now we're going to look inside the barrel, or sorry, inside the box, and look at the barrels. The lighter colored oak is representing the American oak barrels. The darker one's the French oak, and I'm just specifying them because French oak are known to have thinner oak. The barrels are thinner. So how I sampled, 1 week I would sample barrels 1, 3, and 5, they're in blue. There you go. And then the next week I sample from barrels 2, 6, and 8. So I just alternate between those 6 barrels. Titrating 10 barrels every week would be an insane amount to do for one person. So this was making the project a little more manageable for myself. So now onto the on-site tests that I performed. I would collect specific gravity and pH measurements from the top of the barrel. So this picture is the gravity meter that's going right into the barrel. Same thing with the pH probe. And it was really nice to have like a wireless Bluetooth pH probe. It made just moving around the box pretty easy, which is nice. Note that these measurements are all taken from the top of the barrel. So then I need to collect samples to bring back to the lab to worry about titratable acidity. So I collect samples every other week, as I mentioned, and they're 50 milliliter collections. And those are taken from like the bottom range of the barrel, and those are the tubes that I collect the samples in. So to reiterate, they're sampled from the bottom of the barrel. So once I collect those samples, I bring them to the lab, and I do a titration. So if you've taken any Gen Chem class, I'm sure you've done titration. You probably dread them because they take a while. But for those of you who haven't, that's fine. I'm just going to give a brief explanation of what you need to know to understand my results. So this right here is the burette. It's just a long glass tube that's going to I'm going to put my titrant into it, and that is sodium hydroxide for this experiment. For the sake of this experiment, this is our base. And then our analyte, which is in the beaker, is our 25 milliliters of degassed beer. You can think of this as our acid. So before I add any of the sodium hydroxide to the beaker, I'm getting a pH reading of about 4. And then in order to determine titratable acidity, I slowly add the sodium hydroxide to the beer until it reads a pH of 8.2. And then that volume of sodium hydroxide that I used will then go into my calculation for total acidity. Okay, now on to detection of bacteria. I used Schuh's Lactobacillus and Pediococcus medium. This is really just to detect the Lactobacillus and the Pediococcus that I mentioned earlier. So without adding anything to it, this tube right here is what the media looks like. And then after adding a small sample of beer and incubating for 72 hours at 30 degrees Celsius, this is what one of the tubes might look like. So you see all these tiny colonies of bacteria. I really use this as a qualitative measure of just bacteria health at a given time point. So this was not like the main focus of my research by any means, but it was a fun part. Okay, so now that I've collected data from October through like beginning of April, what can I ask my data? So again, like I started with a very broad question, but it's time to just narrow it down a little bit. So I mentioned the difference in sample locations, the top of the barrel and the bottom. So is there a significant difference in pH from the top to the bottom? Does that matter? Can pH and total acidity be used interchangeably? Are they equal measurements of acidity? And third, how does time play a factor in pH and total acidity? So we'll start with this top-bottom issue. So I'm showing here the sampling location for pH and specific gravity on top, and the sampling location for total acidity on bottom. Okay, so these are our results comparing the pH from the top to the bottom. The weeks here, 32 through 41, they're representing weeks after brewing. So this is the 32nd week after brewing. And this isn't when I started my research, but this is when we noticed, hey, there might be something funny going on with the pH at the top. I think it's different from the pH at the bottom. So we decided to collect pH measurements from the bottom as well, so we could do a comparison. So here we're seeing that the average pH from the top of the barrel is 3.68, and the average pH from the bottom of the barrel is 4.0. And then the gray and the pink region are showing the standard deviations, and it's important to note that there is just a sliver of space between them that shows that they are significantly different. So we are seeing a difference in pH top and bottom. So that was actually pretty exciting. Okay, so why might this be? This is just an idea of what we think might be going on. So as the barrel's sitting on its side, there is a kind of like headspace of air on top. And we think this might be part of the issue of the barrel stratification, or the difference in pH from top to bottom. And this goes back to our idea of facultative anaerobic organisms. So if you look at the picture on the right, you see that the bacteria colonies are growing throughout this sample, but there's a lot more at this top layer right here that's exposed to oxygen. And if you look at the picture right next to it, that's one of our own samples, and it's pretty cloudy on top. That's showing that there are a lot of colonies. They're very tiny because there's not as much food for them to eat around, so they can't grow to the size of these colonies, but there are a lot. So lactic acid bacteria is converting sugars into lactic acid. And there we're seeing that there's more lactic acid bacteria at the top of the barrel. If there's more lactic acid at the top, if there's more lactic acid bacteria, that means that they're producing more lactic acid at the top of the barrel, which means it's more acidic at the top of the barrel, which means the pH is lower at the top of the barrel. So this is kind of our idea of why this might be happening. Future work in this area would be to really just figure out exactly what's driving the stratification. So is this theory correct? Okay, next I'm going into the pH versus titratable acidity as what are they really saying about acidity? So let's go back to the expected trends that I showed earlier. So we're expecting pH to decrease over time. We're expecting total acidity to increase over time. And that's not what we're seeing. They're actually both decreasing. And this was definitely a point of minor panic between the three of us a little little bit. So I'll break these down a little bit. Again, we have weeks on the x-axis, starting with week 17 after brewing. Y-axis, here we have pH, and here we have total acidity. And then I'd like to specify that the error bars are not of replicates. So we actually didn't measure replicates for each day. So I didn't do like a titratable acidity experiment 3 times over of the same barrel. And the reason being, like, a time issue. This is exploratory research. It's not necessarily in our best interest at the time being. So what it is showing, though, the point is an average of all the barrels sampled on that given day, and the error bars are showing the difference between the pHs of those 3 barrels, and same with total acidity. Okay, so we thought, okay, maybe we're missing something. Let's do a correlation plot and see if we can explain this a little further. So on the y-axis, we have pH, x-axis total acidity, and we have a trend line showing a relationship between pH and total acidity. This is taken from a research paper on pH and total acidity in ciders, so it's not like perfectly relatable, but that downward trend is definitely what we would expect. And again, it's not what we're seeing at all. So you're seeing error bars vertically for error in pH, and then horizontally for the total acidity. So why might this be happening? We have a lot of ideas why this might be happening. Might be the top versus bottom problem that I mentioned. We might not even know what acids we're looking at in our titration, which would affect how far we want to titrate it. There might be bacteria that are interfering with our titrations, so we don't do a filtering process from the collected samples to the titration. So that might be something to look at. And then the titration endpoint might not be representative for mixed fermentation. So the 8.2 number that we titrated to, it's well known for clean fermentations, that's where you titrate to. But we're in a different area, we're looking at experimentation, so that might be a source of the problem. So future work in this area would be to study the relationship between pH and total acidity in mixed fermentation. So while we're not seeing the relationship in terms of what a clean fermentation should look like, there might be a way to relate them. Okay, lastly, we're going to look at time and pH. Okay, so first focus your energy on this left half of the plot, the white area. So when we first started sampling, things were kind of looking as we expected. pH is decreasing over time. The error bars are not too large. And then around week 27 and 28, we see this increase. And I'm like, oh, that's kind of strange that that's happening. Kept sampling. Week 29, pH drops a lot, and the error bars are huge. Something is going on here, and I don't know what it is. So very interesting. We're seeing less consistency, larger error bars in the second half of our sampling. And a possible explanation that we've come up with is yeast autolysis. So there's a possibility that the yeast in the barrels might be lysing, breaking open, and releasing ions into the beer. Those ions will affect the pH. They might also be acting as food for the bacteria, which would also affect the pH. This is a future area of study again. So are we actually seeing yeast autolysis? Can our trends in pH over time be explained by yeast autolysis? And the barrel manager at Appleton Beer Factory is saying he thinks he's seeing a similar thing. So it's not just us. This is definitely like a really interesting next step. So to conclude, a big point of this research was to find more questions to ask. So I'm going to outline those questions again. We noticed that there were significant differences between the pH at the top and the bottom of the barrel. So what exactly drives this stratification would be the next question. pH and total acidity do not show the same trend observed in clean fermentations. The question would be, what's the relationship between pH and total acidity and mixed fermentations? And lastly, we may be observing some sort of yeast autolysis. So are we actually seeing it, and can our trends in pH describe it? and I'd like to acknowledge some people right now. So Larissa, I mentioned her. She was the one who sampled with me like every week and was super helpful. I wouldn't have been able to do all of this without her. Deanna and Bobby is my advisors through this process. Whenever I didn't know what the next step was, we were able to talk about it and troubleshoot, and it was really helpful. Appleton Beer Factory for letting me use their space whenever I needed to. Dave Hall, again, for asking troubleshooting questions and teaching the class. It's great. And Daniel Martin for providing me with all the reagents and glassware I needed to do my experiments. So thank you.
Questions?
Lauren,
I missed this, but what were the error bars from again? Because you weren't doing replicates.
right, they weren't replicates. So if let's say 1 week I sampled from barrels 1, 3, and 5, the dot that you saw was the average of those pHs, and the error bars was the error associated, or the standard deviation of those 3 measurements. Yeah, Sarah.
What was your favorite part of this project?
I think sampling was super fun, especially since I had someone to do it with. Because it can get kind of lonely in the lab. But yeah, I think
sampling is another meeting too.
Oh yeah. Yeah. Lauren,
Did you get to try any of the beers?
yes.
Which one did you prefer?
Actually, I couldn't tell you if I noticed differences necessarily. I didn't drink them regularly, so less.
Did you notice any differences in the pH or total acidity between the French oak and the American oak?
We looked at that and we didn't see a huge difference at all. There's also one of the barrels, barrel 2, was kind of our trouble barrel. We thought it was just doing wacky things all the time, and we thought if anything it would be an outlier from the rest of the data, and it wasn't. So we did test that. Didn't find a difference.
The bacteria was different.
What made you, and why are you so interested in beer?
I think coming off of the wine research, it's cool to do something similar to that, and it was more that the opportunity presented itself, and I thought it was a cool project. Yeah. So,
How might somebody look at yeast analysis?
that's a great question. That's the bio end of it that I don't know. That's so foreign to me, but that's a great question, and I think. At least Bobby's mentioned for future work he wants definitely a microbiome student working on that end of things.
Would you do flow cytometry?
Flow cytometry. I think that would be an option.
Number 2 was different in the bacteria though, right?
Yeah, so barrel 2 is different in the amount of lactobacillus and pediococcus added to it. So the amount of bacteria added to that barrel was greater than the other barrel. So that's also why it was different. So, yeah, Dave.
What made you decide to start sampling top and bottom?
So I think what happened was we're measuring pH from the top consistently, and then sometimes I would measure specific gravity first, which would kind of mix up what was on top, and then I'd measure pH, and I was getting different readings. So because of that inconsistency, we're oh, well, I wonder what the pH is on bottom. And also when I measured pH at the start of the titrations from the sample collected from the bottom, that was closer to 4, where my pH from the top was 3.7.
Other questions? Let's thank our speaker again.